What is the difference between boosting and bagging? Bagging bootstrap aggregating involves training multiple models independently on bootstrap subsets of the data and combining their outputs through averaging 10 for regression or voting for classification. It aims to reduce variance by creating diverse model. Boosting, on the other hand, trains models sequentially, with each model focusing on the errors made by its predecessor, thereby reducing bias. In boosting, models are combined with weighted contributions, emphasizing more accurate learners, whereas in bagging, all models contribute equally. Can you explain the working principle of bagging? Bagging works by creating multiple random subsets of the original data through bootstrapping, sampling with replacement. Each subset is used to train a separate instance of the same base model. The predictions from these models are aggregated to produce the final output, typically by averaging for regression or majority voting for classification. This reduces variance and increases stability, especially for high variance models like decision trees. How does boosting iteratively improve model performance? Boosting improves performance by training weak learners sequentially, where each learner focuses on correcting the errors made by its predecessor. After each iteration, the algorithm assigns higher weights to the misclassified data points, making them more influential in the next learner's training. The final model combines all the weak learners with each learner's contribution weighted by its accuracy. This approach systematically reduces bias and improves predictive performance. What is the role of base learners in bagging and boosting? In bagging, base learners are typically strong models trained independently on bootstrap datasets, and their predictions are combined equally. In boosting, base learners are weak models trained sequentially, with each learner improving upon the errors of the previous ones. The combined model gives more weight to the more accurate learners. Why is randomness important in bagging? Randomness ensures that each model in bagging sees a different subset of the data, creating diversity among the models. This reduces the correlation between individual models, leading to a more robust and generalized ensemble. By averaging the outputs of diverse models, bagging effectively reduces variance. How does bootstrapping work in bagging? Why is it used? Bootstrapping works by creating multiple random subsets of the original dataset through sampling with replacement. Each subset has the same size as the original dataset but may contain duplicate instances. It is used to ensure that each base model in the ensemble is trained on a unique dataset, promoting diversity among the models and reducing overall variance in the final predictions. Can you name some popular algorithms that use bagging and boosting? Bagging is most commonly used like random forest, which combines decisions trained on bootstrap datasets. Popular boosting algorithms include AdaBoost, gradient boosting, Xting, XBoost, LightGBM, phases that can CatBoost, all of which use sequential training of weak learners to improve performance. Explain how weights are adjusted in boosting algorithms like AdaBoost. In AdaBoost, all data points start with equal weights. After each iteration, the algorithm increases the weights of misclassified samples, making them more influential in training the next model. Simultaneously, the weights of correctly classified samples are decreased. This process ensures that subsequent learners focus on the harder to predict samples. The final model combines all learners, with more accurate ones receiving higher weights. Why does boosting typically perform better than bagging on weak learners? Boosting is designed to reduce bias by sequentially improving weak learners, allowing each learner to focus on the errors of its predecessor. This makes it effective at creating a strong overall model from weak learners. In contrast, bagging reduces variance by combining independently trained models but does not directly improve the performance of individual weak learners. being phases that can, what are the common hyperparameters in boosting algorithms and how do they impact performance? Key hyperparameters in boosting include the learning rate, which controls the contribution of each learner to the final model. A lower learning rate improves stability but requires more iterations. The number of estimators determines how many weak learners are combined. Too many can lead to overfitting. The max depth of decision regulates model complexity, with smaller depths preventing overfitting, phases that can. The subsample parameter, which specifies the fraction of data used in each iteration, adds randomness and helps improve generalization. How does gradient boosting differ from AdaBoost in terms of error reduction? AdaBoost focuses on minimizing classification errors by adjusting the weights of data points based on misclassifications. Gradient boosting, in contrast, optimizes specified loss function. G means squared error for regression using gradients to guide the training of each weak learner. This makes gradient boosting more flexible and applicable to a wider range of problems. Next, that can explain the trade-off between bias and variance in bagging and boosting. Bagging reduces variance by training models on different subsets of data and combining their predictions, which smooths out noise and improves generalization. However, it does not directly address bias. Boosting reduces bias by sequentially improving weak learners, but it can increase variance, especially if the model overfits to difficult or noisy data points. Why is bagging more resistant to overfitting compared to boosting? Bagging is more resistant to overfitting because it combines models trained independently on random subsets of the data, which reduces variance without fitting to noise. In contrast, boosting focuses heavily on misclassified samples, including potential outliers, which can lead to overfitting if not properly regularized. In random forest, how is feature sampling combined with bagging? In random forest, feature sampling is combined with bagging by selecting a random subset of features at each split in a decision tree. This adds an additional layer of randomness phase that can, reducing the correlation with trees and improving the robustness and generalization of the model. Spaces that can, how does overfitting occur in boosting? What techniques can prevent it? Overfitting occurs in boosting when the algorithm focuses too heavily on difficult or noisy data points, causing the model to fit the noise rather than underlying pattern. Techniques to prevent overfitting include using a smaller learning rate, limiting the number of estimators, restricting the complexity of base learners, CG, shallow trees, and employing early stopping during training.